I'll begin with a word of prayer. Heavenly Father, we thank you again for another weekend. Just pray that you just help us to use this week wisely, what class days remain of it, and I just pray that students would just be wise in their use of time as they're preparing for various finals, and just pray that you be glorified in what we do this day, Lord. In your name I pray, Lord Jesus. Amen. So, I had introduced something called the wedge product. Right, and essentially we introduced a work form. So like the work form of a vector a1, a2, a3 was a1 dx plus a2 dy plus a3 dz, and I also introduced a flux form phi, let's say of b1, b2, b3, it was equal to b1 dy wedge dz plus b2 dz wedge dx plus b3 dx wedge dy. And I started talking to you guys about how we can take the wedge product of these with each other and how they have various nice properties. Like we kind of more or less saw that if we have one work form wedge another work form, we get the flux form of the cross product of the vector fields. And moreover, if we take the work form of A with, say, wedge product with the flux form of, let's say, B cross C, well, then that gave us the dot product, the triple product, if you will, of A with B cross C. You might remember that that's the volume, the signed volume of the parallelepiped with sides, side vectors ABC. All right, so we had all that. And let's see, the wedge product, it's naturally linear, it's associative, but it's got this kind of weird property that it's not commutative, but it's kind of almost commutative. Alpha wedge beta is equal to minus 1 to the degree of alpha times the degree of beta beta wedge alpha. And the degree of a differential form is just given in terms of the number of differentials it takes to make the wedge product of a typical term. Like, is it built from wedge products of 2 dx's or 1 or 3? But today, we need to continue this story and talk about the exterior derivative. And so the exterior derivative, you've actually already done this. We've already talked about the exterior derivative in this course. We didn't call it that, but the differential is in fact the exterior derivative on zero forms. So like, if I have a function, df is, well, it's like, partial f, partial x dx plus partial f, partial y dy plus partial f, partial z dz, right, for f, a function, right? We talked about last time a function, real valued function is technically a zero form. All right, so looking at this in light of that language, we see that the exterior derivative of a zero form gives us what? It gives us a 1 form. Right, because that's what that is. And I guess I could just, take a second right here and say, oh, okay, so in light of that, we already have like a little introduction to vector calculus in this world. We can write down a theorem. It's kind of silly, but here it is. The work form of the gradient of f is equal to df. That's immediate from what I've written, you see. if we take the gradient vector field, which is partial f partial x, comma partial f partial y, comma partial f partial z, and we look at the work form that corresponds to the gradient vector field, well, it's exactly the total differential of a function. All right? So that's how the gradient gets brought into the story of exterior differentiation. Let me give you a slightly general prescription for how we calculate the exterior derivative. It's like this. If alpha is equal to like the sum, this is going to be kind of like general language, which I'm not going to explain. I'll just say that this is kind of like the notation I would use in advanced calculus or something. Here I is what's called a multi-index, so it allows for the wedge product of like many things at once. But anyway, if this is the case, then d alpha is just equal to a sum over I of d alpha I wedge dxi. So here, alpha I is like a function for every multi-index I. So what I'm trying to say here is, how do you calculate the exterior derivative of a differential form? It's actually very simple. All you do is you take the total differential of the component functions. You take the total differential of the component functions of the form and you wedge them with what's already there. So let me actually put this definition, and it's admittedly a sketchy definition, right? Because it'd probably take me an hour to properly unpack that notation for you guys where you're currently at. And that's okay, but let me example here. What if we had, let's say, a work form of, all right, so A1, A2, A3. I want to take the derivative of that. So let me call that omega A vector. All right, so the total derivative, it can be the exterior derivative of the work form of A, is going to be the exterior derivative of A1 dx plus A2 dy plus A3 dz. I haven't done anything yet, I've just written it out. All right, so the definition of the exterior derivative is just that you take the total differential of the component functions. So like the way this works is I do dA1 wedge dx plus dA2 wedge dy plus dA3 wedge dz. But you guys already know how to take the total differentials of functions, right? What is the definition of dA1? Well, it's nothing more than partial x A1 dx plus partial y A2. Sorry, still on 1 here. Partial y A1 dy plus partial z A1 dz. So that right there is all just dA1 expanded out. All right. And rather than write the other two all the way out, I'm just going to kind of like go on the pattern on the first one. I'll do the first one carefully. I'm just going to write down the answer for the other two. All right, so like what happens with dx wedge dx? Remember what dx wedge dx is from Friday? Dx wedge dx is 0. Yeah. So that term's gone. But what you do have is dy and dx, right? So we get a partial y a1 dy wedge dx plus partial z a1 dz wedge dx. And then going on here, the next term we get plus partial x a2 dx wedge dy plus partial z a2 dz wedge dy plus, I'll do it on the other board here. I guess I can fit one more into this board here, plus partial x a3 dx wedge dz plus partial y a3 dy wedge dz. So what did I drop? Like in principle, you got 9 terms here, right? Because each differential's got, 3 terms in it, and each of those, there's 3 of those, so that's 9 total terms. But 3 of those drop out to 0 because dx wedge dx is 0, and because dy wedge dy is 0, and because dz wedge dz is 0. So we only have 6 terms. What derivative has 6 terms in it? So let's put things together here. We have the xy terms. So we've got like partial. Let me do the the yz terms first. So yz. So partial y a3 minus partial z a2 dy wedge dz. Do you know where the minus came from? Why is there a minus there? Because you see the dy wedge dz term right here. I have to turn it over from dz wedge dy to dy wedge dz over here, and that introduced this minus in front of the partial z a2 term. All right, and continuing, we've got plus, let's see here. Next, I'm looking for the dz wedge dx terms. And so like dz wedge dx, well, I've got one right here. That's partial z a1. And then there's another one that I have to get a minus from. I get a partial x a3 from this over here, because I have to flip those over for that term. And then finally, the dx wedge dy terms. We've got partial x a2 minus partial y a1 dx wedge dy. Right? Can you recognize what this is? What are we looking at? What are these? What's that? It's a curl. That's right. Like a mathematical gender reveal party. It's a curl. Sorry. Used to be funnier. Now it seems like a more serious issue. Man, the world's messed up. Anyway, d omega A is in fact, yes, the flux form of the curl of the vector field A. And that's how the curl enters the scene. The exterior derivative of a one form is naturally associated with the curl of a vector field. What's up next? Well, example 2. We could look at the flux form, right, of a vector field, let's say B. Yeah, all right, so let's calculate the derivative of that. So we're talking about the exterior derivative of like B1 dy wedge dz plus B2 dz wedge dx plus B3 dx wedge dy. That's my usual nomenclature here. And so we have to take dB1 wedge dy wedge dz plus dB2 wedge dz wedge dx plus dB3 wedge dx wedge dy. So I'm just going to point out what happens here. So this is like, partial x b1 dx plus partial y b1 dy plus partial z b1 dz, right? That's what this right here is. But what happens when you take the wedge product with dy and dy wedge dz? So you get this and that when you wedge it or wedge to 0, and this and that end up wedging to 0 after you commuted over to match, anytime you have one of the differentials repeated in a wedge product, we can show that that's 0. So the terms with the y derivative and the z derivative on B1, they wedge to 0. All that leaves us with is just the x derivative. All right? So, and the same story repeats for the other two components. So in short, what this gives us is partial x B1 dx wedge dy wedge dz plus partial y B2 dy wedge dz wedge dx plus partial z B3 dz wedge dx wedge dy. But we can factor out these terms because if you look at it, each one of these has dx wedge dy wedge dz multiplying it. Now, let me explain that a little bit. So this one here, for example, I mean, first, it's already just manifestly that here, right? There's nothing to do for the first one. For the second one, see, this x is where it doesn't belong, right? So I have to move that over 1, 2 spots. See that? So when I flip the dx, let me just write out. So like dy wedge dz wedge dx is equal to minus dy wedge dx wedge dz, but that's equal to minus dx wedge dy wedge dz, which of course is dx wedge dy wedge dz. So like, yes, the wedge product is anti-commutative, but because I have to do it 2 times, I still get the same plus dx wedge dy wedge dz. And what happens over here? See this one? What happens with this? It's the same story, but in reverse, right? So I just have to move this 1, 2 spots like that. So I get a minus, and then minus and minus gives me a plus. So I get this. What is that? What is this? I mean, this should be easier for you guys to recognize. What's this? That's the divergence. So there we have the divergence of B. Yeah, so yeah. The divergence is a function. It is a scalar. It is not a vector. Hear me. Do not, in some sort of act of like academic hara-kiri or like some sort of like kamikaze rebellion, like on the final, just commit to the joke that the divergence is a vector. I do not accept this joke on your final. You will not make this joke on the final. You will write the divergence is a function. Like, why do I do quizzes in here? You guys like did not respond to my like, So many people still putting the divergence as a vector on the test. Killing me. You have your test? Of course I have your test, yes. So I have graded. I've done grading on your test, yes. Let's see here. So, okay, so where was I? So there's obviously a theorem here, another theorem, which I'll put up here, and the theorem's what? The exterior derivative of the flux form of a vector field is the divergence of the vector field dx wedge dy wedge dz. And so for differential forms in 3 dimensions, that's kind of it. Because the exterior derivative of a 3 form would be a 4 form, and there are no non-trivial 4 forms in 3 dimensions. All you've got to work with is dx wedge dy wedge dz. So we're kind of out of things to do. So that's the exterior derivative for vector field, for differential forms in R3. It produces from the same notion, the same unified concept, the gradient, the curl, and also the divergence, all three at once. And I guess now we should talk about the properties of the exterior derivative. So like here they are. It's linear. And here's its product rule. Its product rule is really kind of funky. If you have alpha wedge beta, the exterior derivative of that is d alpha wedge beta plus minus 1 to the degree of alpha, alpha wedge d beta. So it obeys what's called a graded Leibniz rule. Sometimes it's plus, sometimes it's minus. All right. So like, let's see here. And then last but not least, and this one's really, really powerful, is that if you do two exterior derivatives, the exterior derivative of the exterior derivative, it's 0. So these are the main properties of the exterior derivative. And again, I should emphasize, you already know how to take the exterior derivative of a 0 form. It's nothing more than the differential. And in fact, you can understand some theorems that we've had in this course in light of the fact that d squared is 0. It explains a lot, actually. So let me look at some of those, like example 3. You guys remember we talked about a differential equation being exact? Do you remember that discussion? We talked about, like, for example, if we have m dx. I think I used f, but I'll use m and n here for a moment. If they had this equal to 0, this is exact, right? If what? If there exists f such that a function from R2 to R, right? The exterior derivative, I'm sorry, the differential of f is m dx plus n dy, right? Yeah.
This must be a 0 or 2.
Oh, that's definitely a 2. Thank you. Muchas gracias. Hey, I had a 2 up here. Up to the degeneracy of my writing of 2. But, yeah. So, what's the case if we take the exterior derivative of f then? It has to be what? If you believe my general identity, d of df has to be 0. But what else is it? You see that? It's also dm wedge dx plus dn wedge dy. Now here, dm is just partial xm dx plus partial yn dy, because we're in 2 dimensions. So the total differential is less adventurous. But you see what happens is you get partial xm dx plus partial ym dy wedge dx plus partial xn dx plus partial yn dy wedge dy. Dx wedge dx is 0, dy wedge dy is 0. All you're left with is partial xn minus partial ym dx wedged dy. That's why we must have the condition that we need what? Partial n, partial x is equal to partial m, partial y. That is a necessary condition if the differential equation is to be exact. This is exactly the same condition we needed for our vector field to be locally conservative. Yeah, let's try this on the conservative thing, right? How about going back to 3 dimensions? Example 4, if we have our vector field, right? If it is in fact conservative, it would be the work form of a gradient, right? And as we discussed, that's the differential of a function. So what condition do we get then? D omega f is d of df, which has to be 0. But what was we just worked it out in example 1, right? This is in fact nothing more than the flux form of the curl of f. So see, the flux form of the curl of f has to be 0. And by the way, these functions are like one-to-one correspondence. They're a bijection. They're only 0 if their input is 0, okay? So if I have that the flux form of the curl of f is 0, that forces the curl of f to be 0. That's the way these things work. Which, of course, is what we know. But you see, now I understand it's just another tip of the iceberg, which is d squared equal to 0. And you can also derive, like our two favorite vector identities. Like, check this out. So, example 5. If I look at d squared on f, in other words, d of df, what is that? Just literal. That is literally the exterior derivative of the work form of the gradient, right? But that's by our theorems. That's the flux form of the curl of the gradient. Aha! So that's equal to 0 because d squared is 0, and that implies that the curl of a gradient is 0. And so, great. We could also try this out on like the work form of a vector field, right? So that's d of d omega f. We worked that out. We said, in fact, that was the derivative of the flux form of the curl of f, right? Using that again. But what's the exterior derivative of a 2 form? Well, we worked it out. It's the divergence. It's the divergence of the flux form. That's exactly the divergence of the curl. So, aha, the divergence of the curl being 0 and the curl of a gradient being 0, those are just two, they just exemplify the equation d squared equal to 0, you see. It's all d squared equal to 0. Yeah.
Wasn't d squared equals 0 dependent on that dn dx equals dm dy?
That is true. There are differential equations which are not exact. So, but if it is exact, that means df is equal to this, right? That the definition of an exact form. So if the form is exact, then when we take ddf has to be 0, which then forces this condition on m and n.
But it doesn't matter what your vector is, the divergence of our curl will be 0.
That is true.
But you wouldn't be able to find that.
Right. In other words, well, there's language for this. I mean, this is the definition. We can make this more precise. Alpha, if there exists phi such that d phi equals to alpha, then alpha is exact. If d alpha equals to 0, then alpha is closed. And so a closed form is one whose exterior derivative is 0. An exact form is one which appears as the exterior derivative of another form. And there's like a theorem here to be stated. D squared equal to 0 tells you what? If it's exact, what does it have? So if exact, then what? If exact, then alpha is equal to d phi, right? So d alpha is equal to d of d phi, which is equal to 0. So if exact, then closed. However, the converse is not true. All right? There exist closed forms which are not exact. We spent like a whole day looking at one of those examples. That minus y dx plus x dy divided by x squared plus y squared, which we integrated to find 2 pi around the circle. That is exactly an example of a form which is closed but not exact. So, anyway, let's see here. Is there anything else I could say about just exterior differentiation? I think that's good. It's a good survey. I should go on. We still need to talk about integration. It is fun to look at what this product identity means when you sort through it for like the wedge product of two vector fields, because it's going to give you one of those like snazzy, like trying to think. If we took the wedge product of two work forms, it's the flux form of the curl. But on the other hand, when we take the exterior derivative of a flux form, it's a divergence. So you're going to get that identity about like the divergence of a curl of two vector fields if you look at this. Anyway, there's lots that can be more can be extracted. I'm just starting this. All right, so that's in a nutshell how you differentiate. How do you integrate? All right. How do you integrate? Well, better make myself some space here. I think the quickest summary I have, since our time is limited, after all, you do want me to start talking about the final and stuff. The quickest summary of how to integrate differential forms is simply drop the wedges. So like definition, the integral along a curve of the work form of a vector field is the line integral. The integral over a surface of the flux form of f is the surface integral. The integral, and this is probably where it's most obvious what I mean by drop the wedges. The integral over a volume of like g dx wedge dy wedge dz is literally just the integral over the volume like that. And there's another, well, let me wait till we get to the theorem. There's one thing to say about like a zero form. How do you integrate a zero form? But it's kind of so peculiar. I should just talk about it in as much as it appears in our later discussion. That's it, though. This is essentially it. We should drop the wedges and do the corresponding multivariate integration. But there's something here, all right? You notice I'm proposing something, which is that for a K form, to integrate a K form, we have to integrate it over a K-dimensional subspace. Or you could say this: a P form is integrated along an oriented P-space, if you like. So like a one-dimensional space is a curve, a two-dimensional space is a surface, a three-dimensional space is a volume. Right? So you guys would like this, right? Because part of the fundamental confusion in this part of the course for you guys is like, I give you a vector field and I ask you to calculate the flux, and then you're like, is that a line integral or is that a surface integral? Like, what are we doing? Because with vector fields, we can either calculate what? Line integrals or surface integrals, right? And if you're a little bit fuzzy, as some of you guys are, you get lost. You start doing one when you should be doing the other, or vice versa, right? With differential forms, there's no chance to get lost. Because if it's a P form, you're going to be integrating over a P-dimensional space. Like, you've got no choice in the matter. If it's a one form, you have to integrate it over a curve. If it's two form, you have to integrate it over a surface. And that's just how it is. But here's the beautiful thing. There's a theorem, and this is the Generalized Stokes Theorem. Generalized Stokes Theorem. It states the following: that the integral over the boundary of a space, let's say M, of a differential form, let's call it alpha, is equal to the integral over the space of the exterior derivative of the form. This single theorem encapsulates Green's theorem, Stokes' theorem, the divergence theorem. And if we extend this discussion to higher dimensions, as we could, if you wanted to, a host of other unnamed theorems, it is the fundamental theorem of calculus. So let me show you how this unpacks. Let's unpack the generalized Stokes theorem for a function. So for a function, we need to think about a curve, all right, which goes from, say, point P to point Q. So we're going to define the boundary of the curve to be the set P to Q. All right? And this is the kind of a little bit, I guess you could say, hokey. But like hokey is not a, some people take hokey to be a positive thing in the state of Virginia. So I don't know, it's kind of confusing, but it's generally a pejorative anywhere else, go figure. So like the boundary of C, let f be a function, the integral over the exterior derivative of the function of the curve. What? Oh, sorry. You're all Cavaliers fans? What?
No, I've never heard that expression.
Oh. Are we all? Huh. It's probably racist or something. I'll need to edit this video. But it's like I was talking to student friends in grad school, and I was just, in passing, was like, you moron. And they're like, oh, that's racist. I'm like, what are you talking about? The Moors? Oh. Oh, well, they are from Spain. It kind of makes sense, all right. But definitely not racist in this country. I mean, not in the general context. I mean, anyway. Okay. We stop working and getting this channel canceled, and let's move on. So this would be what this would mean is f of q minus f of p. And what this is the integral over the curve of, well, df, remember, is omega of the gradient of f, right? Which is then, if you believe my definition, the line integral of the gradient. And that is exactly the fundamental theorem of calculus for line integrals. If you specialize this discussion to one dimension, if you just look at this in n equals 1, that is exactly the fundamental theorem of calculus we learned like semester 1. So the generalized Stokes theorem becomes the fundamental theorem of calculus in its, I would say, base case. All right, so next up, so that was for 0 form. How about a 1 form? Integral, now we got to do the boundary of like a surface, right? And a 1 form, so I'll call it omega corresponding to a vector field f. Allegedly, that's the integral over the surface of the differential of that. But remember what we worked out today, that's exactly the flux form of the curl over the surface, but that is exactly the surface integral. It's the flux of the curl over the surface. But what's the other side of this equal to? If you allow me this short Menge-style calculation here. This is exactly the integral over the boundary of the surface of the vector field. It's the line integral around the boundary. And that is the usual Stokes theorem. Do you see it? Right? The integral around the boundary of a vector field is equal to the flux of the curl over the surface. Now for a 2 form, what do we get then? 2 form, we have, let's say, the integral over the boundary of a volume of the flux form of, I'll say, G, well, that's equal to the integral over the volume of the divergence of the flux form of G. But what is the exterior derivative of the flux form? Is the divergence of the vector field corresponding to the flux times dx wedge dy wedge dz. But how do we integrate a 3 form? We just drop the wedges. So you've just got the triple integral of E, divergence of G. Well, we could just say dv. It's the volume integral. And again, if you'll allow me this short manga-style calculation, the left-hand side here is exactly the surface integral. It's the flux of G over the boundary of the volume. And of course, I hope you recognize this is the divergence theorem, or Gauss's theorem as it's known. So the generalized Stokes theorem simultaneously includes fundamental thermocalculus, FTC for line integrals, the Stokes theorem, the divergence theorem. If we specialize to 2 dimensions, we'd see that it's Green's theorem. All right. Anytime, really, you have a theorem which trades integrals, which trades like the boundary of something for the integral of the derivative over the bulk of something, it's probably the generalized Stokes theorem, written in a different formalism. The way this is proved, the way the generalized Stokes theorem is proved, is essentially just to use the fundamental theorem of calculus and see how it sort of filters through a triangulation of space. Like this notion of taking a set and finding the boundary of the set, that's what has to be formalized carefully. Once you've carefully formalized what you mean by taking a space and finding its boundary, once you formalize this boundary operator, then the proof of the generalized Stokes theorem becomes something that you can do. That's some work. It's not a Calc 3 problem. And I don't always even prove that in advanced calculus, but advanced calculus is where I would prove that if I was to, most likely. All right, so I think at this point I probably need to resort to slides. Yeah. So give me a second here. The beautiful thing about all this is that this language can be used to write down equations of physics. So in particular, well, I'll get it eventually, guys. I guess I probably should warm this thing up while I'm waiting, aren't I? While I'm finding my thing. So I've showed you a little bit about how we can do like second semester physics, like our electromagnetism, flux of electric field, flux of magnetic field. We can do all of that in terms of the flux of vector fields. So I'm trying to find, I should have left it open, my bad. Sorry guys. That's not what I want. Well, annoyingly, I am finding the wrong year to look at. Oh, there we go. All right. Sorry to give you time to think. My bad. Let's see here. So so to talk about electromagnetism in differential forms, we actually have to look at not just R3, but space and time. So the exterior derivative now has 4 terms. There's a time derivative as well. And, oh man, I never talked about the Hodge dual in here this year. Oh well. I think there's one in your homework. I'm sorry about that, but it is bonus. So, so in 4 dimensions, you've got 0 forms, 1 forms, 2 forms, 3 forms, and 4 forms. Now, the 2 forms and the 3 forms, they're both 6-dimensional. Like there's, no, excuse me, the 2 forms are 6-dimensional. There's 6 different kinds. But the 3 forms, there's actually only 4 different kinds. So it's a happy accident in 3 dimensions that the number of 2 forms and the number of 1 forms are the same. It's not the case that the number of forms of different degree are the same in higher dimensions. Anyway, get to the point here. You can write electromagnetism in terms of something called the Faraday tensor, which is formed from like the work form of an electric field wedged with the dt plus the flux form of a magnetic field. So you have this 1-2 form that has the electric and magnetic field both in it. And moving ahead a bit here, we can write, I'll get to it eventually here. I should have told you to get your Dramamine, but my bad. Whoa. Come on. So, long story short, we can write Maxwell's equations, the Faraday's law and the no magnetic monopoles equation, both in terms of the exterior derivative of the Faraday, the 2 form being 0. And we can write the Maxwell's, Ampere's law with Maxwell's correction and the Gauss's law, both in terms of the exterior derivative of a different 2 form being equal to the Hodge dual of the 4 current. And so those 2 differential form equations become Maxwell's equations. And not just that, we can actually we can build the Faraday tensor from the exterior derivative of just a single 1 form, like so. And anyway, I at the end of these notes, for fun, I extend it past 3 spatial dimensions to 4 spatial dimensions. And I use generalized Stokes theorem here on a hypersphere, and have a little argument here, basically extending Gauss's law to like 4 spatial dimensions, and you end up with the electric field is Q divided by 2 pi squared r cubed epsilon naught. So like if your electric field it spreads out into 4 dimensions rather than 3, instead of having an inverse reciprocal law, you end up with an inverse cube law. And of course, the significance of the 2 pi squared r cubed is that that's the surface volume of the hypersphere. So like one of the problems in the bonus is trying to kind of poke at that. But the last problem in the bonus is on that. Now, like I said, guys, don't even try the bonus thing if you still have studying to do. If you wrote the divergence as a vector, do not do the bonus homework. Like, focus on other things.